This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning, everybody. I'm going to start right when the recording started because I have some catch-up from last week. We need to cover more today, so let's get into it so I don't have to run over time. But before anything, again, a little bit of admin stuff. So the assignment 3, we formed, the groups already formed. You can maybe see them on LMS. Please double check that you can and let me know if you can't. So as already said, the groups will be of 4 to 5 people and will be formed within the same lab you've signed in. But you'll get all the information about assignment 3 next week. So this week you're still working on your individual part of assignment 2. Also next week we will have the guest lecture. I think I was confusing you in last 2 weeks because I kept saying it'll be next week, meaning this week, but it's actually no, it's in week 6, which is next week. So we'll have 2 guest lectures, 2 guest lectures talking about map collection library and ORIN. And then the week after we'll have the mid-semester test. So the mid-semester test will consist of material from lecture 1 till now. The guest lecture material will not be included in the mid-semester test. So everything that's covered in lectures, including today, can appear in the mid-semester test. So keep that in mind. There's examples on LMS, and as I found out, no calculator is allowed. You should be able to do the calculations on your own, in your own head, which means it'll be use some nice rounded numbers, just to make sure, just so you'll be able to do the calculations. Also, sometime through this week, and it'll be on for the next week for your preparation for the test. We'll start with the quizzes. After the mid-semester test, you'll have them available for that 1 week for that specific topic. But I think because we're introducing it later in the semester, it's fair to keep that. If we open it this week, so you can have it throughout the whole next week for all of the chapters that we've covered in these first 5 lectures. Okay, any questions? So, any assignment? Mid-semester test, anything I haven't covered?
How long will be the test?
How long? 30 minutes minimum, but maybe longer. We'll see. I have to decide. Still haven't made it, so. Pardon?
Are the exams already uploaded?
Yes, the exams are on LMS in the resources section. Yes, with the mid-semester test, it will be here, and it will be in the second half, because I understand that some of you have a clash that you already write mid-semester test in some other subject at 12, so we'll write this one at 1 p.m. So it will not start at 12, but at 1 in the second half of this lecture. So we'll do it a little bit reverse on the mid-semester test day. So first we will have the presenters talking about their map review assignment 4, then it will be me talking, and it will be the test in the second half of the lecture, just to make sure that everybody can come and be here for the test.
We still might have an exam in 1 o'clock to 2 o'clock in other subjects, or what can we do?
Okay, well, we'll then have to set up a different time for you, but so far it'll be in the second half of the first lecture. Email me that you have a clash as well, and we'll figure out something else. See how many people will not be able to attend that. Okay, the catch-up I have from last week, it's about network search. So if we're interested in paths, shortest paths, cheapest paths, allocation problems, in principle we have 2 ways how we can search through networks. 2 different strategies, quite opposing, but both, and different algorithms are based on them. So the first strategy is called breadth-first search, and it's a process where we're searching from a start node to all neighboring nodes first, and when we visited all of the neighboring nodes, we will go a level further and visit all the neighboring nodes of the neighboring node. So how it looks in an image, so if I'm searching from point A, first I will look at D and B because they are the first neighboring node. After I've searched my path through the first level of neighbor, I can then continue to the second neighbors, to the neighbors of my first neighbors, until I reach the potential destination, which will be in point F. So this is the breadth-first search. Depth-first search is exactly the opposite, that only when we come to an end of a certain network vertex, then we will go back to the first starting point. So if that's the example, so I'll start with D, I'll continue with E, F, C, B. I can't go any further, so I will automatically go back to the first node, to point A, and see where can I go from there after that. Quite opposing searching strategies. So if we search for an optimal path using this example, so what is the optimal path from A to F? So path of minimal cost. It can be the cost of the fuel. Which way would you go? AD, AB, no? ADC. Yes. Yeah. So in this small example, it's easy to do it manually. We can see that, we can do the calculations ourselves, but for larger networks, we need an algorithm. So before I'll introduce you to one typical algorithm, but before all of that, there are 3 different optimal path problems that we need to distinguish. First one is talking about the routing, where we're trying to find a single route from one single source to one single destination. That's the first optimal path problem, called the routing. Second one is that we're trying to find a route from one single source to all other vertices. We're creating something which is called a spanning tree. And a third option, I'm sure you've guessed it, is that I'm trying to find distances from all nodes to all other nodes. Then I'm creating the distance matrix. From all vertices to all other vertices. So I create a distance matrix from any place to any other place. So the algorithm for optimal path I'm going to introduce is called Dijkstra. Dijkstra, it's named after a gentleman, a Dutch computer scientist, Edgar Dijkstra. It's a variation on breadth-first search. And it is the most cited paper in computer sciences because it's showing a very elegant solution to a very common problem. This paper is about 2 pages long, which is very little for research papers. But as I already said, it's showing a really nice way, an elegant solution to finding the shortest path. So how does it work? I'm again traveling from A to F, and it suggests to start with the cheapest neighbor of my starting point. So what is the cheapest neighbor from point A? D. Yes, so I'll start with D. Once I found the cheapest neighbor from my starting point, I consider this as settled, as 2 settled points, and then I'll proceed to the next step. So The next step is from these settled nodes, what is the next cheapest path, considering both of them. So what is the next cheapest path from?
A, B.
Correct, so the next cheapest one is B. Again, from these three settled nodes, what is now the cheapest path to go further? Yeah, correct. How about now? And now it's directly F, because if we would connect D, it would actually cost us more to go to the same point C than going the way around from through B. So the final answer is F. So we keep repeating the steps from settling for the cheapest neighbor and then repeat the step for next and next neighbor. The Dijkstra's algorithm is often used for allocation problems, where we're trying to find a portion of the network that belongs together, so we can find let's say the closest hospital to an emergency, the closest hospital to an accident. So that's the example there. So that accident happened, so which emergency team should be sent? And Dijkstra, a variation of Dijkstra algorithm is used for that. And it's done like this, that we first introduce a virtual start node somewhere and connect it with links to our hospitals, with our emergency teams, but give these connections a zero cost. So we've done all this. We can again start with the virtual start node, and then say, what is the cheapest link to my nearest neighbor? So it will be both A and B, but we're starting at one point. The point of this is that we're not running the algorithm twice. We can run it just once. We're only adding one point, but the logic is the same. And then from point AB, for point A or F, we can then decide what is the next cheapest neighbor from the settled nodes, which would now include the virtual A and F. So what would be the next cheapest one? And that can help us directly decide which emergency team is actually closer, because we're including them both within the same algorithm. Does it make sense? Yeah?
So the virtual node just allows us to have multiple starting points, so we can make a judgment on the first time based on the multiple starting points.
Multiple starting points, I wouldn't necessarily call it like that, but if you think about it this way, imagine that the A is virtual and the cost to the next neighbors are just zero, which makes them both, that when I've reached them, I'm not preferring either one of them. So it still have one starting point for the algorithm. The algorithm still thinks that I'm using only one starting point. But technically, yes, I can use multiple. But I'm running the algorithm only once. The point is not that I don't have to run the algorithm for all of my hospitals. I will connect the virtual starting point with all of the hospitals I want, and then run it from that starting point. But because the connection to all of the hospitals cost me zero, they all are the cheapest neighbor, so they will all be in the first round. They will all be included in the first round of the algorithm, but not in the next step. So in the step 2, 3, it will depend. I can slowly keep eliminating them and seeing, oh, this path is actually, it's shorter from here, from the next. Does it make sense? It helps with eliminating the hospitals.
So basically,
Yeah.
why is the question of interest from the hospital at A or F send out the emergency vehicle? It depends on where it wants to send the emergency vehicle.
So let's say the accident happened in point E. Yeah, just think about it. Imagine accident happened in point E. I don't know if if hospital which is in point A or F is closer. The network has the information, but I don't know it. I have to run an algorithm. Instead of starting the shortest route from A to E, as a one algorithm, and then shortest route from F to E as another one, like doubling the amount of calculations, I will introduce a virtual point, a starting point that will connect me with both of my now the first neighbors, so not the starting point, and go from there. So I have the three settled nodes, A, virtual, and F. And then the next round is which one is the closest node after this first round of settled nodes. And we can say it's immediately the F, because it cost me just one, the E, that it's 1. So we've automatically eliminated the point A just with the first round of the algorithm. Yeah? However, it was a good question, because as you can imagine, the dice-class searching algorithm is a radial one. So we're searching radially from the starting point until we reach the end point. As you can imagine, there's quite a few redundant calculations happening for all of the nodes around the starting point. So we have a couple options how to make it more efficient. One would be running it from both directions. That will start the algorithm both from the start and end point, and where they meet, and connect where they meet, and that will be the shortest path. So that's already reducing the number of calculations from the radial, from the big circle, into 2 smaller circles.
Can you explain the radial, why it is radial?
Why it is radial? It doesn't take into account the direction. It just keeps finding the cheapest neighbors in all directions. So it's running, if that's my point, I will run the algorithm east, west, south, regardless where is the end point, where I'm actually reaching. It doesn't distinguish with that.
And how does running it from both ends reduces that?
Pardon?
How does running it from both ends reduce that?
That you're running 2 radial algorithms. Even if you think about the area they cover, it's less than if I will run it for the whole big circle if I run it just from the origin.
In this case also we are not taking care of the direction, but since
Yes,
we are reducing
we're
the
still
area
not
of both
taking care of the direction. But we are reducing the radial calculations around. But exactly what you said is something called A star, Dijkstra algorithm, and that takes into account the direction. So this algorithm prioritizes the network search in the direction of my endpoint, and only if it's not possible to go in that direction, then it will consider other neighboring nodes. Only after I've reached, say, a dead end, that it's more expensive to go into that direction towards the node, then I will divert from that direction and find nodes that are not necessarily in that. So this would be the most optimal calculation.
So I guess the algorithm, when it finds that both routes are the same chip,
Yeah.
In that case, it's going to select both routes. For example, you have 3 options and the price of the cost of the minutes are the same. It's going to select all of them.
Yes. Well, in the original, it's searching that even what's the cheapest path in this direction. But it's not going to help me because it's not in direction towards my point. But the algorithm is still processing that and still remembering that this path can also be the closest one in some case.
For example, if it's bound to go in one way,
Yes,
at
yes.
the end, you
So
always
that-
have the option to go around.
You always have the option to go around, but there wouldn't necessarily have to be the cheapest. So if it's cheaper to go in that direction, it just have a higher weighting in that direction, then it would prefer to go in that direction until you reach the dead end, that direction is actually not going to help you to reach your point. Then it can consider further distance, for example, to go more around, if that will cost you less. Yeah. So the vector between those 2 points as crows fly will then determine the direction. So this is called the rubber band heuristic, if I will just consider the points that are within the direction.
So the radio representation is just because Astro's algorithm doesn't have a particular directional bias?
Yes, no it doesn't, not at all.
Just because of that, it's indiscriminate of which direction to expand the node, so
Exactly,
so
yeah.
just like the brand representation.
This is not, it's a way to search through network, just the search, not direct, not exactly directed towards the endpoint. It's searching the whole network as is. So this A star is more efficient. But there's many more different strategies how to calculate algorithms. So have a look on this website and you can play with some of them. The topic of today are partitions and Voronoi diagrams together with Delaunay triangulations. So what are partitions? Partitions are structures that are dividing space into different parts. So if I'm partitioning the space, it's a strategy that's splitting the space, it partitions the space into smaller parts, or it can be factors, smaller numbers, smaller values, that makes the calculation easier or even possible. So if you imagine our reality and the complicated geometry there is, if we would use it in the most complicated way to explain everything as is, the calculations could actually be quite complex. So we will try to divide this geometric into smaller and smaller pieces. So also one other term I would like to introduce, and it's called the convex hull. And it's the closure of a set of x points in the Euclidean plane. I'll talk about it on the next slide as well, but it's a mathematical term. The very smallest and simplest geometric form we can use for partitioning are simplices. You know this. This is just a different terminology. It uses different names, but it's the same logic as with 0D, 1D, 2D, 3D, and so on. So this is just a naming problem. We're not talking about vectors or networks. We're talking about algebraic topology. That's why we have the different terminology. So the 0 simplex, or you can put in a brackets 0D, is the point. The 1 simplex, in brackets 1D, is a convex hull of 2 simplices, and it's a line. So if I combine 2 points, I get a line. And 2 simplex is a convex hull of 3 simplices, and there would be a triangle. So I'm making the geometric shape from the previous dimension, if you wish, from the set of what I've used before.
Why is 1 simplex then counted as 1D if the line on a space is particularly 2D? If you draw a line on a space, it represents a 2D shape. So it's not a shape, but it's 2-dimensional.
This is not exactly 2D and dimensional space. It's a similar theory. So if you think about it, I'm just putting in a bracket the 1D, 2D. You're right, because line is actually still 2D, but it can also be 1D. So if you imagine you have a 1D chart, if you plot all of your, if you do a 1D scatter plot, it will actually be a line. The points will be arranged in line. So it's the same in here. So the smallest convex set, the smallest convex set, the smallest convex hull, is of 2 points. And it's called the 1 simplex, that's the 1D. So the 0 simplex is a point, and if we're talking about 2 points, 2 1 simplexes, which create the smallest convex, where we have a start point and end point, we can call it a line. And then 2 simplex slash 2D, it's the convex hull of 3 0 simplices. And they create a triangle. There's a condition with triangles, they have to be linearly independent. Because if they are linearly dependent, means they are in one line, they will form a line, they will not form a triangle. That's why there is this condition. We can draw larger structures. I'll talk about it in a few minutes, but then that wouldn't be created from the smallest set of my basic simplices. So these are the simplest geometric shapes you can create with the 1 simplex, 2, 0 simplex, and 2 simplex. It's a point, line, and triangle.
Under the 2 simplex example, 2 linearly dependent and 1 linearly independent to make a triangle. Because 2 linearly dependent will make a line.
Yes, but you have 3. You have to have 3. It's a convex hull of 3 0 simplices of 3 points. Yeah, so 2 points are always linearly dependent. Like that's just a rule. But you need all 3 of them to be mutually independent. But yeah, good thinking. 2 are always in line. There's nothing else we can do about it, but we want the third one to not create a line, so we have a triangle. So the convex hull is a set of number of points in Euclidean plane. And it contains a set of x number of simplices. Then we can talk about face and a boundary of these simplices. Think of this as a theoretical description of geometric shapes. So when we talk about a face of a simplex, it's any simplex where all of the vertices form a proper subset. What does it mean? If we look at this tetrahedron here, this whole triangle ACB form a face. Because all of their parts, the convex hull of AC, this line, AB is a line, BC is a complete line, and the whole triangle itself is a complete subset. There's nothing missing. So the inside is included. Also the line that's marking it is included. That's what we call the face. If you look at a cube, you generally say you can see a face of a cube. There's one thing you should remember, that the line is also can also be a face. This edge is also a face because it is a complete set of 2 points. Yeah, so not just the area of the triangle, but also the edge can be called a face. Then we talk about boundary, which is only the union of all faces, which is again would be this edge, but that's the boundary. This is not a boundary. That's the inside. So it's the face and the boundary. The interior is not considered if we are talking about the boundary. I know this is all common sense, but we have to be careful with the terminology. I myself can mess up what I say, so feel free to correct me. So the conditions are that what we have as a face is a part, that all of it is a part of a whole set of simplices. Are you with me? Might be better if I show you more examples. So all of these things can form a complex, which would be a finite set of simplices. So this is a nice example of a complete complex C, because all of the subsets, all of the simplices, both line and points, are included in that. We have two conditions for what we can call the complex, that each phase of the simplex is also in the whole complex. So if I'm talking about this line as a simplex, is it a part of the whole complex? Yes, it is. As opposed, if I look in here, there is a potential line between this point and that point, but is it a part of this complex? Doesn't look like, because it's not created. The other condition is talking about intersections. So it's either empty or also in C. So this is an intersection of this line, this line, this line, and also an intersection point of both of these faces. Is it a part of the complex? Yes. But we can't see that about this intersection. There is a point which is clearly not marked as a part of this complex. So any of these could then appear in your map as a topology violation. So it's good to have defined finite sets of complexes, not to have unclosed polygons, for example. Yeah?
What does it mean for B and C? Because visually it makes sense what you're describing, that it's within C if the way I'm looking at it is every node is connected and
Do you mean the also in C or the second, the intersection?
I guess the first example you gave from the right top pyramid type structure, is that because the top right edge is not drawn,
No.
the connection is not drawn,
Yes.
it's considered not in C.
Yes. But it's a graphic, it's not ideal, but imagine you would have a structure which would not help to show. There's another example where you can see that you can have defined polygon structures that can be somehow interlocking, but there's quite a few violations in this example. That you don't have defined the point where this line goes through, or will where these three triangles meet. So generally, if the geometries connect somewhere or meet somewhere, it's good to have the points defined so you're not violating your geometry. This is an image that may be hard to imagine. So think of it that because it's not drawn, our eye can still connect those 2 points. We can see that this color has some line, some edge over there. But only what is drawn would be then part of the complex. So think about it that way. So this is a graphical example. In reality or in your GIS data set, it might probably look different.
So is it that basically it has to be sort of like closed figure that all the points have to be connected to each other to consider it part of C? Is that an easier way to understand it?
I'm confused.
Because all these, I'm just looking at all the nodes, and the first
Yeah.
diagram and the last diagram, the difference is that all the nodes in the first diagram have a chain to reach each other.
Yeah, let's think of it that because we've drawn all of the edges and all of the insides of this shape, we've defined all of them. We've drawn everything I could. We've drawn everything we could. We defined everything we could. But in here, we forgot to define that connection. Yeah? So that is not a whole complex.
So does that mean
There's a missing definition of that one connection.
so would you say that the missing simplex is the missing one between the topmost node and the
Yeah, yeah.
node? And
Yeah. So it's not complete. There's some violation of the rule.
bottom right diagram, what would you say for that?
Yeah. Well, there again, this meeting point, this intersection is not defined.
Okay. So that if that would have been a node, then that would be all right. That would be
If there would be a node, yes, that would be correct. It would be similar like this, so that would be considered complex.
So in that case, there will be two lines, one which is completely inside and one which is completely outside. We will consider it as two simplex from that node, like if we have something at intersection.
I would hope it actually would look something 3D. So yes, you could then use it like this. The way I'm telling 3D because I don't want you to think that there would be a shape that is not a triangle. If it would be something that is not a triangle, it's not a simplex. I'll talk about it actually just now. But when we're talking about the simplices, it's point, line, and the triangle. Any other more complex structure is not a simplex. It's a cell structure. But we're starting with the simplest forms you can create, and these are the point, line, and triangle.
Also seems like to be 3D.
You can have 3D, so the tetrahedra is 3D, and it consists of point, line, and triangle.
Or it can be 2D as well.
Yes, yes. That's why I'm saying the brackets 1 dimension, 2 dimension, 3 dimension. The most popular use of simplices is triangulation network, something which is called the TINS, the irregular triangulation network. It's a popular visualization of surfaces. So if we have a field of randomly scattered points and we connect them in triangles, that's something which we call the triangular irregular network.
Sorry to interrupt, but I don't understand the starting point of it. What is a convex hull? What's simplex and complex? Etc.
Okay, well, I'll advise you to do some self-study on these basic algebraic topology mathematical terms. This is not about understanding, it's just you have to take it as a definition. Convex hull is the smallest set of the smallest points you can have within the structure. That's a definition. If you search for a definition of convex hull, there's not much to understand about it. It's a terminology that is used for the smallest set of points that are used for some structure. Yeah. Simplices, there's not much to understand about it. You know the logic if you think about dimensions, 0D, 1D, 2D, 3D. This algebraic topology is only using different terminology. So you can keep thinking about it 1D, 2D, 3D, but with this terminology. Okay? So that's the understanding behind it. I can't really explain you why it's called simplices because it's talking about simple geometric structures probably, but that's how it's called. Yeah, so
is it like the basic unit of measure for this particular?
I wouldn't say measure
For creating
or
any
unit,
diagram,
but it is a basic terminology when you're talking about when you talk about geometry in theory, when you're not actually drawing the geometry, but you're talking about it. Does it make sense? I know it's complicated. It seems complicated because the words are not the ones we hear every day as 1 dimension, 2 dimension, is what I'm saying. You understand it, it's the 1 dimension, 2 dimension principle, but algebraic topology uses these words. So if you wonder, search for convex hull, that's a definition. Search for simplices, again, as a definition, as a mathematical definition. Yeah? Because I'm going to make it a little bit more complex now. I will talk about general cell complex. So we have the simplices, which is point, line, and triangle. But as I'm sure you all know, we can form more complex structures from lines and points. We can, for example, create a rectangle. But that would not be a simplex because it's slightly more complicated. So this is not a simplex, it's a cell. So if we talk point, line, and triangle, simplex. Yeah? If we talk about point, line, rectangle, or any other more complex shape, we talk about cells. Again, you understand this is just a different terminology. So don't worry, you'll get through it. And again, this is a theory on how we can construct. If I would be drawing it using a ruler in a geometry class, you know how to construct triangles from triangles, lines, and so on. So this is a theoretical talk about how to construct a triangle. And then the same, how do you construct a rectangle or different shapes? So again, you have the basic simple simplexes. And I'm using the simplexes to create more complex shape. So I'm using the point simplex, I'm using the line simplex, and I'm creating rectangle in this case. Yeah? So imagine I'm still drawing it on a paper in a geometry class using the simple lines and points, but I'm just creating more complex structures. And it's important to define them in theory because we can do calculations with them. That's why this theory exists. Because computers don't think about drawn geometry, they think about numbers. So if I can define my network or my routes in points, in coordinates, and vectors that would be then connected, I can do calculations. That's why this theory is important to have. It's just not called dimensions. It's not called 1D, 2D. It's called simplices and cells. Yeah? Are you with me? Good.
What was the simplest definition of the triangle figure then? Because you're like, that's the base simplex structure. Now, you were thinking about that in the cell structure.
Yes.
So how would you define the triangle one again?
It's a basic simplex. It's a part of the simplex, the basic simplices of 3 0 simplices. If I have 3 0 simplices independently, that are line independent, I can create a triangle.
And that's the most basic simplex.
That would be the third basic simplex. The most basic simplex is 0 simplex, which is a point. The second basic simplex is 1 simplex, which is 2 points that can form a line. And the third one is 3 points that can form a triangle. But I'm sure you know I can use 4 points and still create a 2D structure. I don't need to create tetrahedrons every time. I don't need to go 1 dimension above. I can have 4 points that can be linearly independent, but not spatially independent. They are on the same plane. Does it make sense?
Then why is it really need to separate the definition of like a triangle structure from any other polygonal shape being made such that we call those categories cell structures? Why is there differentiation?
It's a good question. Might be good to ask to people who invented this theory, maybe because it's good to keep the simplest things in mind for the calculations, like for the triangulation, like for the thins. Because you wouldn't want to do a triangulation calculations using rectangles or hexaeders and so on. But you can use hexaeders for other types of networks, for other things. I would say that it's mainly for the simplification of the calculation.
And we want to have to say 0 simplex is the same point from now on, or something like that? Yeah.
Well, if we're talking about the partition topic, yes.
Yeah.
If you're talking about dimensions, you can still use 1D point, 2D point, like that's fine. But if we're specifically talking, and in exam you have a question about partitions, then yes, you have to use 0 simplex. But if it's a question about random direction or random properties of spatial data, feel free, yes, go back to normal and use the 1D. So, good question. Just wanted to go back. So when we are dealing with cells, so they have more complex shapes than triangles, but the properties are similar. So to understand how we can construct the cells, so again, 0 cell is the same as 0 simplex, 1 cell is the same as 1 simplex, but 2 cell is not the same as 2 simplex, because there is a condition that it has to have more than 3 nodes in the linear independent position. And then we create a polygon, which doesn't necessarily have to be a convex hull. The key why it's not always the convex hull is the word convex. Convex means that it's nice and close, but I'm sure you know we can have polygons that are in an open shape where the inner angle of some of the point is more than 180 degrees. So those polygons are not convex, so we can't call them convex hulls. And we can extend to more dimensions, so we can have the 3-cell would be a closed set of more 2-cell, and so on. So some examples. Again, we have a general cell complex. Same principle as with the simplices complex. Oh, my S's will be amazing after this class. So, same condition that each phase of the cell is also part of the complex. So this is an example, yeah? So if I have drawn means I have defined everything possible, every connection there can be between the points I have. So I've defined the points, I've defined the areas, I've defined the connection between points, the lines. So I can call this a general cell complex. Both of these complexes are also convex.
So, in the definition of the previous slide, it's like a cell is not like a set of the lines doing like a square. Yeah, a cell is only one of the lines. So
No. This is a cell. This whole thing is a cell.
The whole thing.
Yes, the whole rectangle is the cell.
But in the previous slide, you have like
That can, yes,
one
yeah.
simplex. One simplex is a line.
Yes, one simplex is a line, but you can have it as a cell as well. Theoretically, if you think about it, one simplex can be, you can think about it also as the 0-cell structure, a 0-cell complex. But what we will generally be dealing with, we will be dealing with the whole cell, where it includes the 0 simplices or 0 cells, and the whole cell. Yeah.
So
The terminology of 0 cell and 0 simplex is equal. You can use both. Just you have to differentiate that it's not a simplex if it's not a triangle.
Okay, when you are working with a triangle, not
Yeah,
a triangle,
with a triangulation.
For example,
Yeah.
is the same point, you say 0 cell.
You could call it a cell, but yeah, if it's a triangle, you could call it a cell, but preferably you would call it a simplex because it's a triangle.
Yeah.
Yeah.
Triangle or simplex. Here cells.
Here cells. If it's more complex than triangle, it's a cell. Yeah, you already know it when we talk about rasters.
Can we say that the whole thing is a cell, including the whole line?
Is this a cell with 2 cells? The next one.
It's a different level of a cell. So I have a cell in 0 dimension level. So that's the point. It's a cell in 0 dimension. Cell in 2 dimension will be the line. The cell in 2 dimension will be the whole polygon. The cell in 3 dimension will be some other shape. Could be cube, could be something 3D. So it's a cell within a certain dimension. Although we're not really talking about dimension, I know it's confusing, but think about it that way.
Is this 1 cell or is it
This is 2 cells. Let's think of this. This is 2 different cells in our 2D. It's 2 different cells in 2D dimension. This picture shows, yes?
What would be 3 cells, 2 if they look separately, and then 3 as the whole?
Again, 0 dimension, 1 cell. 2 dimension, 1 dimension, this line. 2 dimension, 2 areas of a cell, including their border, including their points. But again, if you think about a country, I'll show the example later, but you can think about it now already, so it will make more sense. If you think about a country, you want the border also belongs to the country. You don't want to say that the country is everything except this borderline. When you draw a shape of a country, if you're describing an island, the coastline is still part of the island. So it's the same here. So the island would be the cell, and the coastline is still included. But if you will take that one single sand on the coastline, that can also be a cell, so that would be your 0 point.
Right.
0 cell.
Wouldn't the whole shape also be considered a cell, like literally one big rectangle with all 6 nodes in that perspective, and then you can also consider 2 cells.
Yes.
There's the left cell and the right cell. And then there's the
Yeah, this is 2 cells in 2D perspective. Yeah? Everything that you see is 2 cells in 2D perspective, and it consists of the lower dimension, of the lower level. The lower dimension is included in that, as it is when you talk about normal dimensions. Okay?
If this is a 2 cell, then what is a 3 cell?
This is 2 cells.
Then what is a 3 cell?
3 cell would be dimension above. 3D shape.
Will there be a box?
Pardon?
That will be a cube or a box? Something like
Yes, that would be a cube. So the 3D cell, if I'm creating a shape, that it's just from cubes. So this is 2 different cells in 2D dimension. If I want to have a 3-cell complex, it'll be in 3D dimension.
So a 3 cell needs to have at least 8 points.
Something like that, just somehow. You need to make it 3D somehow. Yeah, whatever it will be.
So this is a cell in 2 dimensions.
This is
In
2
2D,
cells.
in 2D.
Yeah, in 2D, yes.
And if just considering if that the last point would have been connected and there would have been 2 simplexes, so then what will be the structure? With 2 simplexes and 1 cell. If I connect that and create 2 triangles over there, is it 2 simplex and 1 cell?
I don't know. Let's look at this example. This might help if it's connected. So, is this a general cell complex?
No.
Yes. Yes, it is a general cell complex. Is it a convex hull? No. Good. So this shape is not convex hull because I have this angle there. Okay? Is it a cell complex? Yes. Which dimension I'm in?
2.
2D. So it's a 2-cell complex. Yes, thank you. Is this a cell complex? This line, is that a cell complex? Yes, so it's a 1D 1-cell complex. Can I also call it simplex?
Yes.
Yes. Yes. How about this point?
Yes. It's a 0 cell and also 0 complex.
Great, and the whole thing is just a complex. Just if it's everything included, it's complex. Okay.
But this is cell complex, right?
This pardon?
This is cell complex, not a.
This is a cell complex, yes. This is not a simplex because it has more than, I'm creating a structure that is not a triangle.
But in that, if I'm trying to define cell complex, I don't have that condition of complex cells, convex cells.
You can't always fulfill that, no. Convex cells, you just,
But from this image, we can form simplexes, right?
if I would make it triangles, yes. If I would not make triangles and keep it as it is, then it's a complex. Okay. An example of practical example with tessellation, partitioning, or in other words, tessellation. When we're creating general complexes, there is an allegory on dividing countries in Europe between Poland, showing the Catherine II and the Mary Teresa. So think of it that you're dividing the countries and you want every piece of the land belong to somebody. You don't want the case that one city, one road, one tree would belong to nobody, or that it would belong to more people, because that would cause a conflict. So we're producing partitions by partitioning, and you can think about the countries as an example. And it has two conditions, and it means that they are jointly exhaustive and pairwise disjoint. What does it mean to be jointly exhausted? That all cells together, all of the cells are covered. There is no one cell, there is no one island, no one tree, no a piece of sand that doesn't belong to anybody. Everything is counted, everything is included somewhere. That means that it's jointly exhaustive. So if we think about rasters and they cover the whole area of our map, it's jointly exhausted. Every pixel has a value, every pixel belongs to something. And then the pairwise disjoint means that we don't allow any overlap of the cells. We request that each cell in a raster belongs exactly to one partition. Yeah. There can be joints, they can share the border, but it belongs to exactly one, if you think about it in a one country. Because if I would, as I'd say, if I would have a city or a village that could belong to two countries, I'm causing a conflict. Same can happen with geometries. If I have a point that belongs to two different shapes, I'm not talking about the boundary point, which is a point, that's a conflict. So, of course, in reality, even when we think about the political structure, there are some problems, but ideal case. Yeah?
Why are boundaries ignored?
Because boundaries are same as you would think about them in political system, that the boundary is not a specific drawn line, it's not physically there on the ground. Sometimes can be, but generally it's not. Sometimes they do build a wall or something, but generally it's an ideology. And that's the same for the geometry. It's an ideology between two shapes, two different states. So that's what we've created. But I don't know. Generally in Europe, if I go to a border between Czech and Germany, there is no line, there's no wall. So I can keep walking through the forest and I'm crossing imaginary line. That's why the boundary can be shared. And the points would belong to both sides, but it's more of an idea than actually a physical space. It might make more sense when we will talk about some triangulations in the second half of the lecture, but...
The thing in a raster, the boundaries are well defined.
Pardon?
In a raster,
Yeah.
the boundaries of a cell
Yeah?
are well defined. Are not like...
Yes, so the boundary is defined of the cell. You have the edge of the cell. So that can be the boundary in the raster. Let's just talk about some regular partitions. So we already know, as you talk about raster, the first regular partitions we know are in the raster model, which is, again, it consists of cells. So we can have a square or some other kind of rectangle. Just thinking where I have the image, yes. And if we connect the midpoints of all edges in our partition, we will get something that is called the vertex figure. I'll show you an example on the next slide. And a regular partition, it's a partition where we know that all polygons that are being used are regular and equal. It will be better understood with the example. So we know that this is a regular partition, the triangle. So regular partition, and it's a simplex because it's a triangle, it's a partition, but triangle, simplex, okay? And if I connect the midpoints of every edge of this triangle, I also get a regular shape, and that's called that vertex figure. The red line is the vertex figure. Using squares, again, this is a partition, but it's a cell. It's not a simplex, it's a cell. And if I divide the midpoints, I also get a vertex figure. There's only three shapes that we can call that would contribute in some regular partitions, and that's triangles, square, and hexagons. You can't find any more regular partitions, any more regular shapes that would also have the regular vertex figure. So you can try it yourself, you can do some drawing. And then we also have irregular partitions. There's every other partition there can be, basically. I will talk about some of the irregular partitions after the break. So, thank you for listening this first half. It'll get even more interesting in the next half. So let's have a break for 5 minutes, and then we'll continue with our presenters of assignment 4. I'll put up the list who's presenting today. So just 5 minutes. We've got quite a lot to cover. Yes. So this is the list. Yes. And then I'm going to have the down this way. This is still
together. Remember all.
With equal angles.
This is two set non-convex. This is two set of non-convex.
you don't have to divide it.
This is a cell. This is a cell. Two cells. Two cells.
Two cells. Yes, two cells.
This is two cells non-convex. Two cells non-convex. This is two cell convex.
Yes, you got it right. It's regular. Direct figure is created from the regular direct figure. Figure change the point. The regular polygon. Right, it can be any shape, any regular. No, regular that means what she was showing. Sorry, like this is not convex. Because you have an angle that is bigger than convex.
So not necessary to less than 100.
Yeah, so it is a cell, but it doesn't have to be convex.
So when I say one, that's a line.
So this one
It's not, the convex is not defined. This image is a bit confusing, so think about it, the line is short, it means that if it's defined, then we can call it everything that can be defined.
For the triangles, three surfaces, which makes sense.
Drawing is really hard because thinking about it's not defined.
Why that makes that.
You don't have this information about the connection between Okay, let's start. So we have our presenters today. I'm not sure why do I have 18. Not sure why there's 18 slides, but there's definitely not 18 people. But we'll see. So if I can invite today's presenters. This is not working, show full screen. Set up the timer. So again, if you can click for the next one. First, one can come.
Can I start now?
Yes.
Hey guys, I'm going to present my review on an article published by express.co.uk. The article talks about the effect of the wildfire in the Amazon rainforest that causes the degree of carbon monoxide to increase in the Southern America. So there are a lot of things missing in this map as seen on this slide, but there are 2 points that I want to emphasize in this talk. The first one is the legend. So in the article it is said that the most area with the highest carbon monoxide is on the red patch, but from my perspective I think it's better to use the darkest one or the lightest one to emphasize the extreme points. And the second one is that there is no legend as such, so we are not able to know where the yellow ones and black ones and red ones, what are the values of this area. So, okay.
Thank you.
Hey guys, so the title of my article is Amazon Fires Map, How Much of the Amazon Rainforest Has Been Lost by Ravaging Wildfires, so the same as the previous one, published by express.company.uk last 23rd August 2019. So basically these are the essentials from the review. Area estimation is the geographic information highlight through the map that they have created. Another point is no clear mention of how the area was actually measured by the website. And in addition, the purpose of visualization is in conflict with the choice of projection because it's obvious that they use Google Earth as reference, but Google Earth uses for data projection that preserves the shape but not the area. So the area that they reported is questionable. And also inconsistent unit of measurement because the distance labels are in kilometers, but the area reported is in acres. And also necessary map elements are missing on the map that could have improved the communication of the map to the viewer. And last point is this could have been validated if we can choose a good satellite image and apply spectral band processing. So that's all. Thank you.
Hi everyone, I'm Ricky. So today I want to talk something different. So recently, as you know, like Trump planned to buy Greenland from the Denmark, and the BBC showed this map. So I really want to focus on is this about the scale. As you can see, the Greenland in this map are much larger than its actual, and the actual size is the map on right. So actually, Greenland is about 1/5 of United States. And if BBC posts a map like this, which might shows like a great ambition of the United States government, so I really want BBC to post a map with the equal area projection, because this map is a map with the equal distance projection, which has good area position, but we will have distortion in the area of the country. That's it. Yeah.
More Amazon fires.
So I find an article from BBC News about the massive fire in Amazon rainforest last week. The article contains a map of the active fires in Brazilian Amazon. Some information is properly referenced. For example, the symbols and the colors usage are reasonable. Green representing the areas and the red dots representing the active fires in 48 hours to 22nd of August. This map clearly displays the information of Amazon fire sites, have good composition, and contains scales and legend. However, some information is not properly displayed. The legend locates at the upper left corner, which is not very noticeable. In addition, the map is missing some basic information such as title, detailed source information, and the spatial reference system information, and detailed location names such as name of adjacent country's name. Thanks.
Hi, so I'm talking about an article titled Cold Weather and Windy Conditions to Linger in the South and Bushfire Tears in the North. So in this article, he explains what causes the temperature difference between the South and the North. So the map is a temperature map which explains the weather properly. But the problem with this map is the labels cannot be properly visible, the labels of the temperatures. And he rendered this using the actual BSCH weather forecast, but he forgot the legend, which it's hard to see what the levels of the temperature are in this map, and also the labels he could have added so it's clearly visible which part of the Australia are we actually, or what are the city names. Yeah. And also, yeah, that's all. Yeah. Thank you.
Thank you. You can finish before the time. That's fine. Thank you. More Amazon fires? Anybody? Is this you? What do you mean? If you send it to me this morning before 8 a.m., I can put it in. If it's after 8 a.m., then I have not updated it. Sorry. Does this map belong to anybody? Is this somebody's slide? Really? Okay, well. How about this slide? Owner of this slide? It's interesting the people. It might be the same, I don't know. Oh, this is what happens. So if somebody sent me a slide in PPT, not a PDF, I've had to convert it to PDF. So if it was not one slide but more, as it seems that this is the case of more than one slide, that's what happened. So that's already some points down, I'm sorry. But who is the owner of this slide with this map? Is that you? Okay. So just come on, explain.
Okay. This mathematic map shows the active fire in Amazon, Brazil during the first fire. Back to that time, I found in the BBC News. The geographic information is pretty good reference and streamlined. Although there is no title on this map, the legend is clearly showing the schematic, and the color of the active fire point is red, has strong contrast with the background color, the green. However, there's no north arrow in the map. People may be confused with directions. On the other hand, active fire symbol allows the stem without any contrast enhanced in the size or transparent or color to show where the active fire is serious or not serious. The geographic information is objective testable. Because of the strong reference information, readers can learn the wide range of the active forest fire, through its dense dense active fire point and can realize the serious situation of in the Amazon. Thank you.
Thank you. More Amazon fires.
More Amazon fires.
Not that we wish that for, but
Good afternoon, everyone. So coincidence, it's really crucial because the Amazon is a lot of our homeworks. So look at this map. A lot of IP points, and I make some conclusion of this map. Use different transparent grid to indicate the boundary of the Brazil. And the agent not clear, and they use the BBC used the raw satellite map from Google. It's more accurate, and this might be easy to understand how severe the fire happened in Brazil now. But there are also some negative points. For example, the title is missing. The title, because this is part of GS issue, and another is data lossing. And the north arrow missing, another crucial thing, and the pinpoints overlay too much. It's hard to identify which case is on fire, and Amazon not marked. So that's all. Thank you.
is the person who created this slide here, please? Thank you. Please come forward.
Hello everyone. I found this map from this website. This map shows the recent fires in the Amazon forest. That has some advantage and disadvantage. For the advantage, the map has a clear title, Amazon Forest Fire Start, and also it has scale bar, 1,000 miles on 1,600 kilometers. So we can measure the real distance. In addition, the map identifies main location and significant location. However, the map also has some shortcomings. Firstly, the map data is missing, so we cannot verify the accuracy of this data. And this map also misses some map elements like legend and north arrow. So we cannot indicate the direction of this map. All in all, map also still can be improved. Thank you.
Good afternoon, everyone. And I'm sorry, this is the Amazon fire again, and it is show the map shows the carbon monoxide density in the air, and the merits of this map is the first one is well-designed color scheme, and another one there's no unnecessary features, including north arrows and scales. I don't think it is important for this map. And the issues is that the land-sea boundary is not clear for the dark blue with the black color. And another one is there's too much classes for the carbon monoxide density. And the last one is it failed to show the main cities affected by the gas. And I also have some ideas about to improve this map. Just the classes and make the locations about cities. Thank you.
Thank you. More fire. Anybody?
Yeah. Hi guys, so this is not Amazon fire, it's a mountain fire in mountain range near in California. So as you can see from the map, the author is, I think, quite lazy. He just put a label over there. It's quite ambiguous because we don't actually know where the fire is. The map is simple enough to convey the idea of the fire, but there's no legend, no scale, no compass, nothing. And the article also mentioned about how much the fire spread and where is the evacuation center is, but the map doesn't mention in the map.
Perfect.
Hello everyone.
This is again about the Amazon forest fire, and in this article they talk about the scale of the fire and how massive the forest fires were. So they used different images and maps to talk about it. First they used a satellite image showing how the smoke has spread all over the continent, but we do not have the names of the location of the countries that are affected. So, and in other images as well, we see they lack a lot of map elements like scale bar and legends. So we do not know how much area was covered, which the article was actually talking about. And in the last image you see they talk about the smoke in terms of aerosol optical depth, which is measured in some nanometers, but the article actually doesn't talk about the aerosol optical depth. So it is something which is irrelevant. So
Great, thank you. Hello everyone, my name is Chiting Su. Today I'm going to introduce this graph, and this graph is sourced from in BBC News. The article describes a critical town of Syrian civil war that has fallen into government force-spawned rebel force recently. And the town is called Khan in Idlib province, as you can see in this map. I think the advantage of this map is that it provides a clear title and source, and the legend also explains very clearly. The map uses different colors to show the areas that are controlled by government forces and other rebel forces. The high contrast colors that readers understand the boundaries quickly. However, there are some drawbacks. Firstly, there's no fundamental elements like the north arrows, scale and spatial reference frame. Secondly, it doesn't provide the whole area map that this map reference from. So readers may feel confused about where this area locates in the Middle East area. And thank you. Thank you.
This article is from BBC News. I also want to use this map to show how many people are affected in this power cut. The map has clear title, source, and labels. It also shows the number in shadows of color, but it forgets the reference frame, the scale, campus, and the name of the white part. It also doesn't indicate the creator of this map. I didn't find similar map in their source, but I found some data from the report of National Grid, which show in this table. Compared with the map, the table is more detailed and the map missed some data. For example, the number of people affected in SP Energy. It's marked as unknown in this paper, but we could find the number in this table. And the author also add up some data for simplicity, such as the UKPN is divided into 3 parts in the table, but also add this all to only show one number in this map. So I think it's a great map. It's not contain some misleading information. So that's all.
Thank you.
Hi everyone. As everybody talked about this, I want to talk about this in other aspect. We all know that geographic information is served for some politics or like economic views. So actually, do you remember that in this BBC view, there is a sentence say that activities says the president support them to use the tree clear support. The president support them to do the tree clear activities. So they cut so many trees to burn them to use for factories. But the president said he didn't support this. President after that he said he don't have enough resource to put out the fire. So I think the BBC News actually, from a perspective, hints that the president maybe have some problem or the politics is not right. He needs to change. Can I have more 30 minutes? Seconds? Thank you. So, on the one hand, the BBC News want to show us that how bad the fire it is. Use these two pictures. You can see this. Everyone know the element. I want to say that again. You can know the fire is so severe. The carbon monoxide is so strong. But on the other hand, he pointed out this. In 2019, we have more number of fire than other parts. So actually, that's what the BBC News want to say. The president maybe have some problem, corrupt, something like this. Okay, thank you. That's my answer.
Thank you.
No, I want to say something.
Thank you for explaining the situation. Yes. Quickly. I have a lot to cover as well. So. Okay, I would like to ask you for paying as much attention as you can because there's more things I would like to explain. And I don't want to go over time, and next week we have the guest lectures, so it wouldn't really be that good if I'll have my slot before their slot. So, remember how we talked about cells and partitions? Hopefully you do. Because now we're talking about something that can be derived from that. And there's a case of structures which are called Voronoi diagrams. In other terms, these can be called Thyssen polygons. And we use here also the term of dominance, and that is the spatial dominance. So we are interested in the area of dominance of a point compared to another point. We're trying to find the nearest point, the nearest side to some other point. It will hopefully make more sense with images, which I'll show you in a minute. So in this slide, in the first equation, we're calculating which area P, which area is P dominant. So I have a point X, and then I have either area P or Q. So I'm basically comparing the two areas, area P and Q, which one is dominant, and that is that the distance of my point X, P, is smaller than the distance between point X and Q. It looks like I have a slide about it afterwards, so let's just know that. So I have this is my site P and site Q. Think of it as the catchment of a hospital. So these are the two hospitals, and then I have a point X somewhere there. And I'm trying to decide which area of dominance this point X belongs to. Image like this, so I can see that the distance between X and Q is bigger than between X and P. So if this is the border, with a better color, see better here, it will be the border between the P and Q. So there's another, like a whole area. So that's what I'm talking about. So this is the P dominant area. I'm trying to find if the point X belongs to it. So, okay. Other terminology that the boundary I've just drawn, it means that points that are exactly on the boundary have the same distance from P to Q. And then a second condition of a Voronoi diagram, so one is the dominance area, and a second condition is regions. That Voronoi diagrams form a region around the cell, a region where all of the cells, all of the points that are within this cell are closer to P than Q. So I'm defining a region, area of dominance and the region. It may seem like it's similar, but you can see that the dominance is part of the region definition. So dominance is finding where does the point belong, and region is defining where all of the points belong, if it's cell P or cell Q. And we'll have more images, so it'll hopefully make more sense. But how do I create Voronoi diagrams? So imagine I have a random set of points. This is my field of random points. So I randomly pick two of them. So I pick those two. I draw a connection line. This is just theoretical helping line, connection line. And then we create a center line from this connection line. So I pick 2 points and then I create a center line. Now we can remove the connection line and keep the center, the line that went through the center. Then I pick another 2 points and create a center line. Connect them and remove the helping line. However, I'm not interested in these lines, I'm only interested in this segment of the line, so I can remove that. This is already showing me some boundary, some region around this particular point. So it's creating the boundary between the region, between this point and this point. In the first case, we're creating a boundary between this point and the top point.
Why do you select those points?
Randomly. Just because, yeah. Pardon? Well, it's exactly where they meet, and I also know it's exactly where they meet. But I also know that this boundary is after already existing boundary between from the first connecting from the first creation of the center line. Make sense? If I know that this boundary is after this one, and this is the one I was constructing, I'm interested primarily in this one. Then I can just remove that one.
So we kept the first point as the same. So the first point of the line is comparing it with the second on the right. Rule the midpoint and then
Yeah. You connect 2 points, drew a center line, and then
keeping one point reference as much as possible so that we can isolate it.
Pardon?
We're trying to keep one point as reference and connecting it with everything else until we can isolate it with one. Because when we isolate that,
Yeah.
we can look at other points,
Yes.
their relationship with other points.
Yes.
And then isolate it.
Yes, seems like you're getting it. That's good. There's a property of this border point, of this central point, that the distance is exactly the same. Because, as we said, one property of the Voronoi diagrams that the boundary is right when from between 2 points, between 2 sides, where they have the boundary, the distance is exactly the same. If you think about it in practical terms, if you live right in the middle of 2 tram stops, you would then have to decide which one you go. But if you're right in the middle, you would ideally want to go to the closest tram stop. But if you're right in the middle, you live on the boundary of what is the closest. Yeah, so that's that's the same principle here. So the property of this point, of this inflection point, is where 2 boundaries meet, and it's a point where the distance between those 2 points is the same and the other 2 points is the same. Now I'm continuing with construction. Again, I'm connected 2 other points, created a center line, and deleted what I don't need. The segment, only the segment I'm interested in. And so on. Until I've created something just called the Voronoi diagram. So I'm partitioning the space into a specific way using the Voronoi diagrams, where I know that any point within this polygon, the closest distance of point within this polygon is to this side. Nowhere else. Same for this, any point within this polygon. The closest distance to any other point in my point field is this point.
How the diagram decide which part of the line you have to remove? Because you said this is what you don't need, but what is what you need?
You remove the ones where you need your Mac frame, like you would have here. If this is my edge, I will remove anything that is outside of my Mac field.
Some lines are intersecting another.
Pardon?
For example, two slides before that. Yeah. In this case, why you decide to remove that part of the line and not the other part?
Why am I deciding to remove this part?
Yeah.
Because I'm interested in a border between those two lines. This line is not this line is not.
But it's helping to the border of the other. It's defining the other.
It's helping the border with that one, but this one is closer. So I still need to find the border between the red one and the other black one. So this line is just irrelevant.
Is the point of border diagrams supposed to actually reach as a point on the geographic space? So there's only one particular region?
Basically, yes. So this is I'm defining nearest neighborhoods. I'm defining catchments for hospital or catchments for schools. So each school would have the nearest catchment, or each hospital I would have again have the nearest neighborhood.
So you keep the line that you is closest to the new point, and you're removing the part of the line that is closest to other spots.
Yes.
Yeah.
Yeah. So remember which points are you're interested in, and if it's a line from another point, that's what you're not interested. So you can remove that one. Then you create something like this, where you have Voronoi cells. An example of 10 shots in a city, based on Euclidean distance. Again, you have the edges of the map. But as we know, we don't have to calculate distance only using Euclidean distance. We can also use, for example, Manhattan distance. We think about the street network. So this would be, so the shapes, the borders would look differently. So if we look at this example, so imagine that this is a network. So the polygons that are in the background are looking at the network distance, not as the crows fly distance. So this actually was not constructed the way I've shown you, how you connect two points, but you're calculating the distance on a network and finding the middle point in the distance from point A to B in the network. You find the middle point, and that's where you will split that shape. So this case is an example of a network distance Voronoi diagram. Yep.
So is this are the lines being drawn between B2
So,
and B2?
yeah. This case is a geometrical, because I'm connecting 2 points and creating a geometrical center line using the Euclidean distance basic geometry. Then there is an example where I can use different distance, like Manhattan distance. And in this case, I'm using the network distance. That I will actually calculate the length of a network link and then see where is the middle and cut it in the middle of this length in a network. Not in this crows fly, not the direct line.
Did you say length is just distance, or it can be any cost?
Yes, it can be a cost. Yeah, you can use cost. You don't have to use distance. You can have it based on the cheapest way to get to certain locations. Yes, that's true. That's an example, but yes, this is based on the distance, on the network distance.
By network distance, would mean the edge cost to get from one point to another, or just
Just the three of them: the blue, red, and yellow.
Just those three.
Just those three, yeah, because you have more points here, but these are the connecting points. So you calculate this between P2 and P3, and you know that this would cost you, or it's pretty much almost the same distance
faster, so I can go within the same distance, I can, within the same time I can get from here, or it will take me that long. Yeah? And then if I think about Voronoi diagrams, I can have something which is called a dual graph. So based on what is nearest to our side points, to our seed points, we can create a dual graph. So it's another way of looking at our geographic reality that is derived from Voronoi diagrams. So if we think of the faces of one graph, and you all agree that this is a graph from the network theory? Yeah? So this is a graph. If you look at the points and the edges, it's a graph. Yes? So imagine I have points here and here as well. It's a graph, graph. And then if I correspond each face from partitioning, each face of this shape, each face of this cell, and if I collapse it into just one point, in this case it would be the side point, or it can be a center point in many ways, but I would represent this whole cell by only one point. Yeah? Condition. So if I collapse it or make it corresponding only to one point, and then I connect these points, I will get something which is called the dual graph of these points. And it's actually a triangulation. Again, when I collect them. So each cell corresponds in a vertex in a dual graph, and these vertices are connected in our original cell, share a boundary, they share one simplex. And if we do it consistently, we get the wide triangulation graph. It's dual because you can derive the one from another. So if I have Voronoi diagram, I can derive the dual graph, the wide graph from the Voronoi diagram. Or if I don't have the Voronoi diagram, but I have a triangulation of some sort, I can calculate the Voronoi diagram from that.
But it will be based on a function, right?
Fun?
If I convert this graph,
yes,
the first graph to second one, it's based on some function, because you said you can have a centroid also as one of the points. So centroids also as one of the points. Right now, over here, these are the points which you connected and created the second dual graph.
Yeah, if I will use centroids, it will be a different dual graph.
But so basically you can convert from one to another based on some function.
On some definition, yes. But
and
yes.
if you want to go from that to back to the original one, you need to reverse that function.
Yes. Yeah. Exactly. And the function I will be talking about is called Delaunay triangulation. I'm just looking at the time, but let's go with it. It's a special kind of triangulation. Generally, there's so many ways. If you have 3 points, try it yourself. If you have a field of many points, there's multiple ways you can create a triangulation. So many ways how you can connect many points in a triangle. Delaunay triangulation is a special triangulation. It's a dual graph from Voronoi diagram, and it has these main conditions. And it's that it has the smallest circumcircles. Triangulation, I'm creating triangles with the smallest circumcircles. And also, I'm creating triangles with the largest minimal angles. What I mean by that, couple points, so I can create triangles like this. So for this first one,
it doesn't necessarily have the smallest angles. It's not as compact. So if I connect my poles this way, the circumcircle is smaller for both cases, and also the angles are smaller. It's the difference between the angles. So in the red case, this angle is quite big. The difference between this one and this one is bigger than the difference between the green ones, between these three. The difference between the green angles is smaller in their size than the difference between the red angles. So these are the two main conditions of Delaunay triangulation. Smallest circumcircle. So you can see that the green one is much smaller, and the smallest difference between the inner angles. And they are always a convex hull. Do you remember what's convex hull? It's a closed triangle, convex hull. Good. So mathematically we can say that the Delaunay triangulation is a triangulation where each of the triangles has a smallest circumcircles and largest minimal degree angles. And largest minimal degree, I mean the difference between the angles is minimum. Okay? Example, we have set of points. I pick 3, create a triangle, create a center of this triangle, and compute a circumcircle. I introduce the 4th point. However, the problem is it's inside a triangle and it's inside the circle. That means I cannot keep the original triangle. I need to split the original triangle into 3 and replace it with 3 other triangles and create new circumcircles. Have the conditions of the Delaunay triangulation. To fulfill the conditions of the Delaunay triangulations, that I keep having the minimum smallest circumcircle and the minimum difference between the angles. It means that no other point is inside another triangle or inside the circumcircle. The points always have to be outside. So if I introduce this point, it's outside the triangle, but it's inside the circumcircle. So what I do, I create different, connect the points, wait, what do we do? Connect the points differently, and redo the circumcircles this way.